I'm just gonna clear the page here. Okay. So our next question is asking if the length of the diagonal of a rectangular box must be L, what is the largest possible volume? So when it's asking for largest possible, right away this is telling me that this is an optimization problem. So most likely we're going to be using derivatives. So we can draw a simple coordinate system just to represent our box. It looks something like this. So this is the coordinate system where Z, X, and Y. And we have to figure out how do we find the largest possible volume for a given value of L. So L would be from the diagonal, so it would be from the origin to this point of the box. So it would be coming out of the page here, and it would be, I'll just make this in red. So from the origin to this point. So I'll make a bigger box just so it's a little more clear here. So if we had a giant box, oops. Like that with, so this is just a larger image, so this is just expanded out into this bigger box. We're saying from this point to this point is our L. L value that we are trying to find the largest possible volume, like the value of L when it's the largest possible volume. Okay. So to start off, we would want to define some values for what the volume is in terms of x, y, and z, and the value of L in terms of x, y, and z. So we know volume is 2 sides of the square times the height. So here in a coordinate system, volume would just be equal to x times y times z. So this is just each length of the box times itself to give you the volume. And then the length of L for any kind of point in space from the origin, it follows the format that the length, so here the red line, L squared is equal to x squared plus y squared plus z squared. So this is for any point in a plane. So L could be any other point in a 3D plane or a 3D coordinate system. And it would be in this format. L squared equals x squared plus y squared plus z squared. And that gives us what the value of L is if we square root the x squared, y squared, and z squared. So here we can go one step further and say that L is equal to x squared plus y squared plus z squared. And from this we can kind of substitute the value of z into the value of the volume. So volume, we have one equation here. We have one equation, and then we have another equation. So we want to substitute them into each other to kind of find an equation that has all the variables in one equation. So we have here volume So volume is equal to, so we're going to substitute here z, and we're going to use this equation to find what z is. So if we rearrange it, this would give us z equals L squared minus x squared minus y squared, all square rooted. So here we'd have x times y, and then z is this value right here. So it would be square root of L squared minus x squared minus y squared. I'm just going to draw a line so you can see that these are different. Okay. So now we have the equation that we will be optimizing. So we're optimizing for volume. I believe it said the largest possible volume. So we're looking for the largest possible volume here. So the first step here is we would take the derivative with respect to x, and then we would take the derivative with respect to y, because these are the two variables left in our equation. So here the derivative with respect to x is equal to, so here we can see that it's kind of a complex formula, so we would have to kind of use the product rule, which is the derivative of the first. So there's two components to the volume, this component and then this component. So we say the product rule is the derivative of the first, so xy, times the second, plus the derivative of the second times the first. So we'll go through this step by step. So here we would say the derivative with respect to x for the first term is just y. And then that will be the derivative of the first, and then times the second, which is just what's given above, L squared times x squared minus y squared. Sorry, L squared minus x squared minus y squared, square rooted. And now this is the first component of the derivative, and then the second component is the derivative of the second. So the derivative of the second part, the L squared minus x squared, which is it's a little more complex, so we'll leave that as so plus, and we'll do that in a second here, and then it will be times the first. So we would multiply whatever the derivative is of the second component with xy, which is the first. So let's just think about what the derivative of this is, the second component is. So we would have to use the rule of kind of the derivative of the outside times the derivative of the inside, because we have the square root. So to simplify it, we know that the square root of x, the derivative of that is 1 over 2x. So we know this is true for a simple just square root of x. So this is just something you would have in a derivative table, or you'd have already memorized. So knowing this, so the derivative of the outside component, so the square root, would be 1 over 2 square root L squared minus x squared minus y squared. So we have this component, and then times the derivative of the inside here. And the inside is L squared minus x squared minus y squared. So the derivative here would be negative 2x, because that's the only, we're doing derivative with respect to x. So it will be times negative 2x. So I'll just put this in bracket. So this is just a multiply sign. So I'll put a dot for multiply. And then we can see that the 2's cancel out, and we are left with negative x over L squared minus x squared minus y squared. So this just gives us the derivative with respect to s. So just to clean up this line, we're going to clean it up to put in the final format. So v prime x equals, we have the first component, y square root L squared minus x squared minus y squared, and then minus, so this, so we have this left. So we have minus, we have the two x's, so x squared, and then the y, and then the bottom is right here. So we have L squared minus x squared minus y squared. And we kind of cleaned it up. So let's erase the top here to continue with the solution. We'll leave the equation on the bottom because we'll need that for later. Okay. Okay, so now we found the derivative with respect to x. We want to put it in a format that's kind of in one unit so we can find the common denominator and just combine these two terms. So we have vx prime. The common denominator for this is just this. So we take this denominator and multiply this component by the same. So we'll multiply both the bottom and the top by L squared minus x squared minus y squared and L squared minus x squared minus y squared. So we'll multiply the first component by this to find the common denominator. So we'll do that right here. So we know the top will be, because we're multiplying square roots, it'll just be bracket L squared minus x squared minus y squared. And then the bottom will just be the same. Square root L squared minus x squared minus y squared. And we also have the term here, so it will be minus x squared y. Okay, so sorry, that's not really on the screen here. Minus x squared y. Okay, now we're going to put all of this together, so it will be equal to y bracket L squared minus 2x squared minus y squared. And the denominator would still be the same. L squared minus x squared minus y squared. Okay. So we found the simple format kind of for the derivative with respect to x. So here we would do the same thing, find the derivative with respect to y for the same initial equation. So our initial equation was, let's see here. So our initial equation was this equation right here. So we're going to do the same thing, but we're going to take the derivative with respect to y of this equation. Okay, so we'll end up with, so we follow the same idea. So the derivative of first times the second plus the derivative of second times the first. So you can see that it'll end up being a similar format to this, with the y and x's switched around because the y and x in both terms are in a similar power. So here we would have derivative of the first, which is y, times the second, plus the derivative of the second, which we said is derivative of the second here will be what we'll do in a second, and then times the first, so xy. So we did the same thing, so we do the same thing here. So the derivative of square root L squared minus x squared minus y squared. So we're trying to find the derivative of that with respect to y. So we know the format that this is, the derivative is 1 over 2 square root y. So knowing this, we'll do the derivative of the outside, which is 1 over 2 square root L squared minus x squared minus y squared, multiplied by derivative of the inside component. So it would be multiplied by negative 2y. So the 2's cancel out here, and then we're left with dy prime is equal to y L squared minus x squared minus y squared minus the second component, which is y squared x over L squared. So we'll combine both of these terms to get just one component, one term in the derivative of the volume with respect to y. And we'll end up with the following. So we'll end up with x all squared minus x squared minus 2y squared with all squared minus x squared minus y squared. So this is kind of the derivative of the volume with respect to y. Now that we've completed this step, so we have this equation, and then we have this equation, which are the two important equations that we need. Okay, so I'm going to clear the page here. Okay. So to maximize the volume, we need to set one of these derivatives to 0. That way we know where the value of where the values or the terms x and y exist, such that it's maximized or minimized, and we'll find this out in a second. So we'll set y L squared minus x squared minus 2y squared. So the derivative of volume with respect to x, we'll set this to 0. And then we'll, we know that we can just multiply out the bottom, so, and we can, we see that at y equals 0, we can't have that as a solution. So if we had y equals 0, then the volume would just be 0. So we have L squared minus x squared minus 2y squared is equal to 0. So we multiplied both sides by the denominator, and we've got rid of the y because at y equals to 0, the volume would just be 0. So we want to see what the volume would be when we look at this component and we set this component to 0. Okay, so this is kind of our first equation. So L squared minus x squared is equal to 2y squared. So we'll call this equation 1. And then we do the same thing for the derivative of the volume with respect to y. So we have x L squared minus x squared So actually, this is the opposite. This is the derivative with respect to x, and this should be the derivative with respect here. Let me clarify that. So the first component is the derivative with respect to y, and then the second component is derivative with respect to x that was set to 0. So here we have y minus L squared plus 2x squared minus y squared equals 0 over this. So the same square root, same idea here. I'm going to write that out because we're just going to multiply by it on both sides of the equation, and then we know that at y equals 0, same as above, when x equals 0, the volume is 0, so we would now have a maximum. So here we are left with the equation that we want to maximize. So we're left with L squared minus 2x squared equals to y squared. So this is our second equation. So now we substitute equation 2 into 1, and we'll have L squared minus x squared minus 2 L squared minus 2x squared equals 0. And then we're just going to try to solve for x in this scenario. So we have just have negative L squared, and then we have negative 3. And we have actually. So here we have L squared minus 2L squared, which is negative L squared, and then we have negative x squared minus negative 2x squared, so that would be plus x squared. Oh, so actually that would be 4. So 4, positive 4x squared plus negative x, so that would be 3x squared equals to 0. And now we have the first kind of solution of our problem. We have 3x squared is equal to L squared, and then x is equal to, so we'll divide both sides by 3, so we'll get L squared divided by 2, but sorry, we'll get L squared divided by 3 on this side, and then we'll also square root this to get rid of the squared, so we'll square root both sides, so if we had x squared, we'll square root x squared to get x, so this will give us L over the square root of 3. So that's the value of x. So clear up some space here. We'll leave the important equations. So now we plug in the value of x in equation 1 or 2. So let's say we plug it into equation 1. So we'll say L squared minus L over square root 3 squared equals 2y squared. And now we get, so if we said L squared minus L squared over 3 equal to 2y squared, we'll get 2L squared over 3. So we're taking 1L squared minus a third L squared equals 2y squared. And then we know y squared is equal to L over 3. And then knowing this, we'll know y squared, sorry, we have a squared here as well. We know y will be equal to L over square root 3. So I'm just gonna, here, I'll just erase this right here. So this is our equation 1. We know that y is equal to L over square root 3. Okay, so we have the value of y and x where the volume is maximum. So let me just clear the board here. So when x equals L over square root 3 and y equals L over square root 3, we get a maximum volume. So we go back to our original equation for z. So z equals L squared minus x squared minus y squared to find out the equation for z, because that we still need that component to solve for the volume. So we know here square root of L squared, and then we have L squared over 3, and then L minus L squared over 3. So here we have, if you ignore kind of the L squared, because they're the same for each component of the term. So here we have 1/3 L and another 1/3 L being subtracted from L squared, so 1 whole L. So 1 whole L squared minus a third L squared minus another third L squared will leave us with a third L squared. So we're left with square root L squared over 3, which will give us L over square root 3. And that's the value of z where the volume is maximum. So we know previously volume is x, y, z. And we can see that x, y, and z equal the same value for the maximum volume. So we'd say L over root 3 times L over root 3 times L over root 3. This would give us L cubed on top. So L times L tells it. And on the bottom we have 3 times the square root of 3. So our question is, if the length of diagonal rectangular box must be L, what is the largest possible value? So we've finally gotten to our last solution. The volume is equal to L cubed over 3 square root of 3. So we've classified the maximum volume in terms of L, and that's what the question is asking us. So we followed the same format to the solution presented. This solution is correct, and it follows the correct way to find the maximum volume. Great job. Solution is correct.